if you're looking for the area between two curves, we're establishing dominance really more than anything else, which means that you're looking for the curve that's physically above another curve, if it's with respect to x. If it's with respect to y, you're looking for the curve that's physically to the right of another curve. All right. So I'll show you what that looks like in a sec, but I'll just run through the process first. Find the point of intersections, establish dominance, and then really what you're going to do is just integrate the difference between the two functions. You'll find that we've been doing this all along. It's just been a hidden step. Because whenever you're finding a definite integral, you are finding the area between two curves. The issue is one of those curves has been the line y equals 0. So if I had something like the definite integral of x squared, it's really x squared minus 0. Otherwise, what would happen is you would get an infinitely defined area, I suppose. It would be like there's no bottom to it. So the area under a parabola, well, there's a whole lot of under a parabola. So there would be infinite space, I guess you could say. All right, so it's got to get capped off somewhere. It's implied that it's the x-axis, but really it's more explicit than that. It's because you're cutting it off by subtracting 0 from the original function, which is the x-axis. All right, so it's been a hidden step all along, so there really isn't much of an adjustment here. All right, and in fact, making use of absolute values makes this even easier. But you do want to find at least some semblance of an understanding of where the contained region is. All right, because we're looking at a line and a parabola, an upward-facing parabola. And again, we're into sketches at this point, not point-by-point graphs. All right, and we have a line with a positive slope. It definitely does not look anything like this, but it doesn't need to. We just need to have an idea. All right. The only way that it's going to bound any area, contain any area, enclose a region, would be if it looked something like this. Yeah, the slope is probably pitched a little higher, but then again, I don't know what the scale is of this quote-unquote graph. All right. I do know that the line is the dominant function over this interval. All right. So here is the relevant interval going from this location to this location. I need these points. All right. Keep walking away from it. All right. If I could find those points, I know where the bounded region starts and where it stops. I know what the dominant function is. I know what the non-dominant function is, and then I'm off to the races. All right. So I'll start my integral. My integral is going to look like this: 4x plus 45 minus the parabola. So parentheses x squared plus 2x minus 3 dx. I just need the lower and upper bounds. All right, and that's going to come from these intersection points. If you're doing it by hand, well, you haven't been listening. That's really what I'm getting at. Because, yeah, I could find the intersection between a parabola and a line, set them equal to each other, and solve. But I don't want to do that. Right? I don't want you to do that. Okay, so we're going to type in our equations. Get rid of this stuff. We have 4x plus 45. Oops, wrong field. It really doesn't matter, but I'm going to put the one that's physically more dominant in y1, and then the one that's non-dominant I'll put in y2. So x squared plus 2x minus 3. All right, I'll take a look at the picture. All right, by looking at the table, I can get a sense of the neighborhood of the graph. It looks like they start getting close to each other in the -6. Well, actually, it turns out they're exactly the same at -6. So we're looking at values that are close to 0. So I'm going to go for my window. I'm going to type -10 to 10. And then I'll use that nifty trick of zoom fitting the y min. So clear, zoom 0. right, so that's the graph. It looks nothing like the one I created, but it gets the job done, or at least the one I created gets the job done. So intersection points, because it's nice in this case that the values come directly from the table. It's really nifty, but you can't always count on that. So we'll do a quick second trace 5, enter, 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 to get our first intersection point, which is -6 for x, and second trace 5, and then I'll get over to the next intersection point as close as I can, or as closer to the second intersection than the first intersection, which is a +8. So now I know my intersections. All right. So when I'm computing my integral, I now know that I'm looking for, when I hit math 9, an interval beginning at -6 and going to 8. And it's the difference between 4x plus 45 and the quadratic, but I have 4x plus 45 stored in at y1, and the quadratic stored in y2, so I get what I need that way. I'll label up the integral on the whiteboard in a second. But the other thing is, and it's kind of a consequence of what we were talking about in the previous pages, is that if you're not really sure about the dominance component of it, let's say you thought maybe it was the other way around. If you're ever unsure, just throw absolute value brackets around it. So let's say I thought it was y2 minus y1. And you'll get the same thing. So I'll math frac this bad boy, 1372 over 3. And so what I'm going to do is just mark this up a little bit. -6 to 8, that's what this was, -6, and this was 8.